Hello, in the study of the Coarea formula, we are at a point where we need to justify the particular definition of the Coarea factor given by this determinant. We have to see where it comes from, what its geometric significance is, and prove a few facts about it. The starting point for us will be a very useful fact indeed for the whole proof of the Coarea formula, and that is the following. The Coarea formula follows from its special case of G equal characteristic function of A, where A subset of Rm is measurable. Of course, Lebesgue measurable. And if we need, we can also add that, and the Lebesgue measure of A is finite. We can always do that by looking at intersections of A with cubes of integer side length. So that is saying that in this formula star, if you prove this formula star for these particular G's, then you have the formula for all measurable non-negative G, or just all integrable G's. And that is basic approximation tricks of measure theory. You replace arbitrary measurable G with summation of characteristic functions of measurable sets. But what does star become when I apply it to this G equal characteristic function of A? So as I write down the equation, you can follow along with me and see if you agree with me that the formula star for this G becomes integrating the Coarea factor dfx dlmx only along the set A, and the right hand side becomes integrate Rn. Now I'm integrating the characteristic function of A against dhm minus n measure and over the fibers. So this will become this, the fiber intersected with A, and then I have dln of z. So that is my claim that if you prove this formula double star for all measurable subsets of Rm, then you get the formula star for all integrable G. Okay, that's a simplification often done in the proof of the Coarea formula, and this will be useful to our investigation of the Coarea factor. Okay. Where does determinant dfx transpose square root come from? How would someone think up this strange definition for a Jacobian? The answer is consider double star, which we call the Coarea formula again, for linear maps f from Rm into Rn. Indeed, the proof in the Federer's book and in Evans and Gariepy is based on the idea that if you have a Lipschitz function, then it is differentiable by Rademacher's theorem, so you can break up the domain into pieces on each of which f is very well approximated by a fixed linear map. Then you compute either side of the Coarea formula, by that I mean now double star, for f, and then for L, because these are by Lipschitz comparable, you get good estimates. And then you know that the Coarea formula holds for the linear maps. From that, you prove double star up to some error that goes to 0 if you do an exhaustion. Therefore, the proof is based on first confirming the Coarea formula for linear maps. And when you look at the linear maps, you see you end up in a natural way with this quantity for the Jacobian. This is the only value that will make double star true for a linear function f. Or we will later switch to L notation. Okay, so at this point, I actually invite you to forget that we know the Coarea factor of a matrix or a linear map is given by the determinant L transpose root. And we want to get to this quantity by organically investigating the double star formula rather than cheating. Also, I am identifying linear maps with the matrices in the standard basis. So in this identification, the adjoint operator of L is also L transpose in the matrix form. So I'm having this identification implicitly throughout. Okay. The first observation, so our goal is to discover this C and L formula on our own. The first observation is whatever C and L is, it must satisfy the following. For every A subset of Rm measurable. Okay, I'm going to copy the formula double star. So this will be integral of the Coarea factor L dLm over A must be equal to integral over Rn hm minus n of preimage of the function, which will be L inverse of z intersected with A dln of z. But this is equivalent to, so L is a linear map, and its derivative is again L. For linear maps, the derivative coincides with them. That means at every x, the derivative is L. So this is just a constant quantity, and therefore that comes out of the integral. And then integrating over A is just Lm measure of A. And I don't have simplification for this side, so I keep it as it is. So this will be L inverse of Z, preimage of a singleton, dln of Z. So we don't know, we forgot that we know what the CNL is. Rather, we want this property. We expect this from C and L, that for every measurable A, this must be satisfied. At this point, we don't even know if actually this is a well-defined constant. Does there exist such a constant that only depends on L, such that for every measurable A, we have this equality? So our job is prove such a quantity C and L exists. We know if it exists, it's unique, so we won't discuss that part. And then prove that indeed C and L is none other than determinant L transpose square root. So task 1, task 2. Okay. Approach 1. So this video is coming with some gap compared to the latest video I uploaded, but for good reason, because I did a thorough investigation of this Coarea factor and looked up different references for how they have approached this. So I'm going to present multiple ways of doing this, and each approach, of course, has its benefits. Some are more elementary than others, some give more information, and I thought this would be a nice collection of all of these in one place for future reference. So approach 1 is quite an interesting one, and what you do is define mu of A to be the right hand side in so I think at this point I have 3 stars. Okay, so take that in the integral of the measure of fibers to be the definition of mu A. For every measurable A, this is some number, and then prove that mu is a Borel measure on our M, of course. Prove that it is absolutely continuous with respect to Lm, which means that mu of A is 0 if Lm of A is 0. Okay, this follows from the Coarea inequality, which we'll have a separate video on. Prove that mu is translation invariant. This is rather easy because we're talking about linear maps, and when you shift things, it will be quite easy to see that nothing changes in that integral, and also that mu is not completely equal to 0. For some sets, it's positive. Then we have this uniqueness fact about the Lebesgue measure. Because this, I think actually you don't need to prove this one. It's a technical task, and we don't really have to have it for the argument to work. Then by uniqueness of so this is not completely uniqueness. You need the condition that the measure of the unit cube be equal to 1 or something. So up to a constant. So by uniqueness of the Lebesgue measure, or the translation invariant, okay, translation invariant measures, there exists a constant C positive such that this positivity is where we need this condition that mu is not just 0, such that mu is a constant multiple of the Lm. And that is exactly saying the 3 star holds with this C. So this C and L, now 3 star holds with C and L equals C. So that's an interesting way of proving that the Coarea factor is well defined and it exists. The merit of this approach is that in some non-Euclidean contexts, similar trick has been done. For example, when you discuss Coarea factor for maps between Carnot groups, or between arbitrary rectifiable metric spaces, as in the work of Ambrosio and Kirchheim. But we won't actually get into the details of this, but it is an interesting one on its own. So what is our second approach to discovering the Coarea factor on our own? Okay. An important observation. In the equality CNL, this is just 3 star that I'm repeating for your convenience, for Lebesgue measure Lm of A equal Rn Hm minus N L inverse of Z intersection with A dl and Z. So remember, we want to prove that there is a CNL, which makes this true for every A. So the observation is that in the equality this neither quantity, either side depends on the coordinate system on Rm. So you have this set A, and you have the fibers of the linear map, which we will see shortly that are in fact affine. So my picture is actually quite correct. So I don't have arbitrary curly preimages like for arbitrary Lipschitz functions, as we've seen before. So when you compute LMA, it doesn't matter if your coordinate system is this way or it is positioned this way. So that's the left-hand side. For the right-hand side, the measure of the fiber is actually, it is the Hausdorff measure, and it only depends on the metric on this set itself alone. It doesn't even depend on the fact that this is embedded inside the bigger Rm. So that is truly independent of the coordinate system. And then this integral is not happening on this Rm domain. It's happening back here in the target Rn. So we have this target space Rn, and here we have Rm, and I intentionally do not commit to any coordinate system yet because I don't know which one will be the best. But what I have confirmed with this observation is that it won't change anything if I switch to a different coordinate system. Okay, and that simple observation will have a significant effect on our following analysis. Okay, the next observation, okay, if I may call it, is that for any z in Rn, so you have to imagine these z's being in this space, L inverse of z is a shift of the kernel of the linear map L, which we will denote K throughout. So let me first draw this kernel. Okay, this will be my space kernel of the linear operator, and the kernel of course passes through the origin, so this will be O. And I'm also assuming for the majority of this presentation that rank of L equals n, so it's not a degenerate linear map. So the case where rank is strictly less than n can be directly handled. So I leave it as an exercise. You have to prove that those integrals are 0, and which is quite easy. So throughout I will have this assumption. So this K will be m minus n dimensional, because the image of the linear map has dimension n, the maximum possible. So exactly m minus n dimensional space is mapped to 0 by L. Okay, and now this observation 2, where does that come from? If you have two quantities, two vectors or 2 points on the same preimage, okay, so this is proof of observation 2. Suppose x1 and x2 both belong to the same preimage above z. Then, so f is L. Then L of x1 equals L of x2 equals z. From this, because L is linear, so we're of course using full strength of linearity, is 0, and that means x1 minus x2 belongs to the kernel of L. So every x2 in the preimage is x1 plus y for some y in the kernel. So if you shift the kernel by the vector x1, you get the preimage on top of z. So x1 is just any point on the kernel. And in my picture, so this blue part is x1 plus the whole space k. So as z changes, either you remain on the same fiber or you get shifted to another parallel copy of L. So that's the picture that you should have in your mind. Okay, now I put a system of a coordinate system on my space Rm, and I take k to be m minus n many of the contains the m minus n many of the standard vectors, and then I take the orthogonal complement of k to complete the coordinate system. the precise way of doing this is to take an orthonormal basis in K and another orthonormal basis in K complement, orthogonal complement. Then put them together, and that's an orthonormal basis for Rm. So as we did in observation 1, all the quantities concerning this 3 star are the same, although we have switched probably to a new coordinate system. And now you see that the geometry is particularly simpler, especially the Fubini's theorem is glaring at us right there. But how do you get that out? That is what I do right now. Okay, some small notation. Let T from this kernel complement to Rn be just the restriction of L to K complement. And remember that this is n-dimensional. Then T is invertible. And we will identify this with Rn. So this is an invertible linear map from Rn into Rn. In particular, its determinant, and we'll need absolute value, is well defined. So what is happening here? Okay. What's happening here is that we have kernel of L complement. So this is effectively the part of the space Rm where L acts in non-trivial way. And it maps, of course, or T. So when restricted to this, we have given it a new name. This will help actually to avoid some confusion with notation. So here's Rn. So when restricted to this orthogonal complement, L in fact is just an invertible map, and this is the actual part of L, because if you look at, so here is 0. If you look at any other vector sitting here, the action of L on X is equal to the action of L on this projection of X to this complement. So this is really getting to the heart of the linear map L. And this has connections to polar decomposition, if you are familiar with that. Okay, and how am I going to use this to my advantage? So here is 0. So I need orthogonal complement. Oops. Okay. So it's a bit hard to get orthogonal complement of n-dimensional spaces, but of course that's just my excuse. And my set here, my set A was like this. So this is my set A, and these were the fibers of my linear map. Okay, now I want to compute this integral. So I want to prove the formula 3 star. So I integrate over Rn, and this is the target Rn, Z happening here, the quantity Hm minus n, L inverse of Z intersected with A, d ln of z. And here I am integrating a function over this space, and I have a linear transformation t between this space and the space here. So I can use the change of variables formula in its simplest form, or this is basically just how the Lebesgue measure scales under this t. And the result will be that this will be integrate over this pre-image Rn, which is just k complement, so maybe this is better notation. This quantity here will be, okay, z, let's say, comes from this x. So z is t of x, which is L of x. So this will be the fiber above x, so this will be times Rm minus n intersected with a. So this function, a function of x, is exactly equal to this function of z. It's the same under identification via the map t. So, or you can say this quantity is the pullback with t of this function of z. I'm just doing a change of variables formula for integrals. And then comes the determinant of the map t, and this becomes dln of x. So I translated an integral on this space to an integral on its pre-image. But now determinant t is a constant and comes out of this integration. And then because I'm talking about, so the pre-images, these sets are just affine subspaces of Rm minus n, basically. These are just Lebesgue measures of those sets. So this m minus n Lebesgue measure of x times Rm minus n intersected with A. So of course there's this universal identification of each one of these fibers with a copy of k, which is Rm minus n. So this becomes that. But now we have Fubini's theorem. If you integrate the measures of the fibers along the shadow or projection of the set A, you recover the Lm measure of the set A. Now we have the formula 3 star with the quantity determinant of t. So this calculation, what has it proved? It has proved the two tasks we had. I mean, maybe one of them only. Number one, that there exists a well-defined constant, so in this case here, with which we have this 3 star equality for every measurable A. So we've proven that the formula 3 star holds with this quantity determinant of t absolute value. This completes the existence of the Coarea factor. Our task 2, which is to prove that this determinant t is equal to determinant L transpose square root. Okay, so Okay, what I have in my notes is based on this. So I will need this picture, not surprisingly, many times. So let me get this erased. So I give you also time here to think about how you would prove that the absolute value of determinant of t is the same as the square root of this strange determinant. Okay. Lemma that I'm trying to prove is that absolute value of determinant of t is just determinant of L transpose, or L conjugate, now that we have been playing around with the coordinate system. Okay, proof. In this mu coordinate system, the matrix representation of L is, okay, if I write this matrix in this coordinate system, if you pick from the K, so here will be the matrix representation of T. Okay, so this will be a block here. And so what you take is you pick this X, you write its coordinates in the orthonormal basis that we have, the red ones. Then the map T with its corresponding matrix takes it to some vector in the target Rn. But okay, so the end result for the L will be n times m vector. So this will be the end of actually the matrix. So this will have the right number of rows. Okay, so this will be an n by n matrix sitting here. But if you take something in the kernel, it goes to 0. So, and here will be the 0 matrix. So this 0 matrix is n by m minus n size. So this will be a square matrix, n by n square matrix, which represents t, and then 0 matrix. So this will be the matrix representation of L. Therefore, the matrix representation of L adjoint is represented by, so let me write maybe L for the matrix of it. So this will be the transpose of that. So this is just linear algebra fact, and it's quite deep when you think about it, but it says that the matrix representation of the adjoint is just transpose of the corresponding matrix. Okay, and then L, it's matrix times L transpose, this becomes an n by n matrix, and guess what? That will be the matrix representation of T times the matrix representation of T transpose. And both of them are n by n matrices. When you take determinant of L transpose, that will be determinant of T transpose, unfortunate notation here. And but this is, because T is a square matrix, this is determinant of T to power 2. And that's the end of the story. When you take root, the lemma follows. Okay, and I have a corollary of. So at this point we are done with the two tasks we had. We have proven that with this quantity we have the Coarea formula for linear maps. But I want to give some more results regarding this Coarea factor, and which will lead to some equivalent definitions of it. Okay. The first one is as follows. Take any parallelepiped P contained in this kernel of L complement. This is just K complement in our notation above. Then the volume of a P, LP, divided by volume of P. So by these I mean n-dimensional volumes of these sets, equals this Coarea factor, which is again determinant L transpose. Okay, that's the lemma. Where is the proof? The proof is just one line. By definition of determinant, this volume of LP over volume of P equals, so the fact that this P is inside the kernel complement is saying that this is just matrix T or linear map T applied to this parallelepiped region. Volume of P, and that is absolute value of determinant of T. But then from this previous lemma, we had that this is equal to CNL. That's the end of the proof. And in some texts, this has been given as a starting definition for the Coarea factor. There's some geometry, of course, behind it, and I had the pictures above. I don't want to scroll too many times up and down. Okay. The next one, which follows immediately from this one, is that Cn of L equals the supremum of the n-dimensional volume of LP over volume of P, where P is an n-dimensional parallelepiped in Rm. Okay, in this case, compared to previous one, we don't assume that the parallelepiped is contained in this. I have difficult time drawing perpendicular lines today. So this is kernel complement, and this is kernel. So in the previous lemma, the parallelepipeds we took were contained already in this set. But now they could be lying in different orientations like this. And the proof is based on the fact that L of P is just L of the projection onto K complement of P. That is because of the picture I showed you before. If you have x here and this is the projection of x, then L of x is just L of the projection. And therefore this is just L of this t applied, t applied to the projection onto k complement of p. K is kernel of L. So if you pick a p and you project it, then this quantity in the numerator does not change. So replacing p with projection onto k complement of p does not change numerator. However, denominator can get smaller. Because when you project, projection is 1 Lipschitz, and a 1 Lipschitz map only decreases the Hausdorff measure. This is saying that a line here, when you project down here, it becomes a shorter line. But it's true in n dimensions as well. Also, this could be the same. It could remain the same if p is completely contained in k complement, which isn't a case ruled out. Then it doesn't decrease. But it never increases. So it can get smaller or remain the same. That's the only possibilities. But it can never increase. Therefore, in trying to get the supremum, so supremum above is reached with p completely contained in this kernel complement. We don't care if supremum is also reached for other p's, maybe not, but we know that there are some p completely contained in this k complement with which this supremum is attained. But the previous lemma showed that this ratio of volumes is exactly the Coarea factor, and the lemma follows. Okay, this is yet another way some texts define Coarea factor as the supremum. This has the nice interpretation that the Coarea factor is the best that the linear map L can do in stretching volumes of n-dimensional parallel pipettes, and the n is less than m, so it's kind of Grassmannian sitting in the larger Rm. Okay, all interesting facts. I also have some exercises for you. And if in future you would like more exercises, please let me know. I can always add some to every video that I make. Okay, let L be from Rm into Rn, where m is bigger than or equal to n, be linear. And surjective. So rank of L equals n. As before, let K be kernel of L. Okay, so let P from Rm, same domain, into Rm minus n, a different target, be a linear map whose restriction to K is injective. Okay. In my picture, this is my K. This is my K complement. So basically P is a map that is not degenerate along this subspace. It could also be non-degenerate in other directions, or can it be? If this is Rm minus n, probably not. So it's kind of saying that, well, if the kernel of P doesn't have to be parallel to either of these subspaces, so it could be like this. But anyway, so the assumption is as clear as it can be. Define a new linear map from Rm into Rm. So same dimensions, where x is mapped to, okay, we have P of x, which maps to Rm minus n, and then we have L of x, which maps to Rn, so that together they become an m-dimensional vector. So this is kind of augmenting the map L. So we attached some new map to it. So we have same dimensions. A linear map between Rm's. Rm to Rm. Okay, so this is all the setup. Now, the exercises that prove that this Coarea factor of L is equal to determinant of Q, absolute value, and then determinant of P restricted to this kernel. It has obvious connections to all we've been saying and the geometry that we have discussed. This says that from determinant of Q, take away the contribution that comes from what P does on the kernel. We don't want to know what Q does on the kernel of the map L. And this agrees with everything we've said that, for example, this CNL is just determinant of the restriction to kernel complement, this map T. A very interesting exercise on its own. And if you take some particularly nice P's, you probably can recover from this the other formulas we had. Okay, and exercise 2. And this is from Nicolescu's notes. Is very similar in spirit. Let L be as above. Let F n plus 1 up to Fm, these are m minus n many vectors, form a basis for the kernel. And let U1, Un form, okay, not form, be such that their image under L, so LU1, LUN, are linearly independent in Rn, so they're the target. Again, I have to go to my picture. Hopefully I get some perpendicular lines here. So kernel complement. So you take fi's belong here. ui's could be in the kernel complement or could have some angle with it, but they are not definitely inside K, because then their image LU will be 0, which cannot be linearly independent. So these are UJs, and the image of UIJs, of course, are here, and they form a independent set. Then this Coarea factor to power 2 equals, okay, are you ready for this? So gram determinant of the vectors A, U, A, U, N. Maybe actually it's nicer if my eraser works. So we take root gram determinant of Fn plus 1 Fm over the square root of the gram determinant of U1 Un Fn plus 1 Fm. Okay, so let me unpack this for you. Remember the gram determinants from the area formula discussion, or if you don't, just look them up. What gram determinant of these vectors are saying, gives us, is the volume that these n vectors form, a volume of the parallelepiped that these vectors form inside Rn. And because they are linearly independent, this is not 0. That's why we need these linear independence for them. And this one here will be the m minus n dimensional volume of the parallelepiped that these form inside the space K. So here is some parallelepiped, here is some parallelepiped, and these two are their volumes. And this, all of this together will be the m-dimensional, the largest parallelepiped that uij's together with these fij's make. And this ratio, the claim is that is always equal to this Coarea factor. Okay, that was my second exercise. One last thing for today is maybe I should also make this an exercise. I have a proof and I had made it ready for use, but I don't want to go on forever. So fix L from Rm into Rn as before, linear. Let H be a change of coordinate systems. That's how I'm thinking about this here. Be a linear isomorphism. Okay. And write L tilde for the map L composed with H, which is again from Rm into Rn. This lemma, which I have not yet completed the statement of, will be needed in our proof of the Coarea formula. So here is Rm, here is L going into Rn, and here is this change of coordinate system. So here is another copy of Rm and H goes here, so their composition is L tilde. If you've watched the implicit function theorem already, then you know where this is coming from, because we will transform our coordinate system for so that an arbitrary C1 function, say f, ends up having vertical fibers. And the derivative, of course, by chain rule is composition of the derivatives. So it's pretty much in this picture here for the derivatives. So if we are going to use that geometry to prove the Coarea formula, we have to know what happens to the Coarea factor under this transformation. And this lemma is answering that very question. So under these assumptions, the claim is that the Coarea factor of this transformed function is related to the Coarea formula of the original one by this formula. So you take determinant of h, that is very much expected, that's h dilates or shrinks volumes, obviously, but similar to previous exercises, the part of h which has to do with the kernel should not be counted in. So you take away the absolute value of determinant of h restricted to this particular subspace. Let me draw in red what is happening. So if this was the kernel of L, then it has become some new subspace back here. So this is the same, by the way, as kernel of L tilde, which is of course H inverse of kernel of L. So when you restrict H to this, it becomes a linear map from this copy of Rm minus n to this copy of Rm minus n. It has a determinant, and we just take that off. So this part has to do with that. But the numerator is the full determinant of how area transforms. So anyway, that's another nice exercise. You can use some of the previous ones to prove this. The one proof I have in particular goes back to this 3-star formula, which is the defining property for the Coarea factor. Write the Coarea formula for the function L, and then transform everything by a change of variables in the integrals under the transformation h, and that will be it. So thanks a lot for hanging on this far. Please write in the comments if you happen to know other ways of finding the Coarea factor, if there were parts of this that you particularly liked, if there was too much geometry, too much algebra, let me know. But this was a very fun video for me to make, a great exercise in geometric linear algebra. Until our next video, have a great one and see you soon.